Simple harmonic motion is often conjoined with waves, so it's usually simple harmonic motion and waves. We're going to try to tackle all of simple harmonic motion today. I'm going to give you guys a lab to do next week. Unfortunately, since we don't have a ton of time in class next week, it's going to be a take-home lab with a simulation. So it's really quick. It is. But that'll be our next thing. Who's heard the word oscillatory before? I'm sure everybody has, because we're in South Florida, and if you've ever lived anywhere that it's hot, everyone has an oscillating fan. Everyone, especially if you grew up in the 90s, you've got an oscillating fan. A fan that goes. If you grew up in the 90s, you also had a sprinkler that went. And that is oscillatory motion. And what that means is the type of motion that goes back and forth from one side to the other, and it passes through an equilibrium position. Equilibrium means that point in the middle where it wants to be, that happy balance point in the middle. For the record, it doesn't have to be horizontal. It also doesn't have to be vertical. It could be in any dimension, as long as it is repetitive, cycles back and forth, and it has an equilibrium position. We saw this word when we were doing rotation, especially orbits. The amount of time it takes to do one complete oscillation, one cycle of back and forth, and that's the place where a lot of people struggle. It's not just back, and it's not just forth, it's both of those guys together, is called a period. It's capital T, and we measure that in seconds. Now, to be fair, it doesn't actually have to be from like one extreme to the other. You could pick any random point in its motion, and as long as it goes from extreme to extreme and back to that point, that's still a period. It's totally fine, not a big deal. We'll look at this word, by the way, phase, in a second. The important part here is to know that oscillatory means motion that is cyclical, motion that cycles. I'm just going to sit. Another new word for us is the word frequency. Frequency with that fancy F, little curly F. This is the number of complete oscillations that the oscillatory motion does in 1 second. In other words, it has units of per second, or 1/seconds. I never remember the guy's name, his first name. Obviously, his last name is Hertz. Has absolutely nothing to do with the car company. Absolutely nothing. I always want to remember his first. I want to say Heimlich, but I don't think so. I think that's very stereotypical. I don't think it is. Heinrich? No, I don't know. I'll figure it out. Whatever. One day. I like knowing science history. I'll figure it out. Yeah, that's what I mean when I say I'll figure it out.
Because you said one day. So.
Yeah, I could do it one day. It won't be today because I got my phone on me, but one day. There is a relationship between the period of oscillation and the frequency. It is a reciprocal relationship. 1 the frequency is the period. You can kind of see that in the units, right? You also kind of see that in the definition, the number of complete oscillations in 1 second. If I flip that, it's, I guess, the number of seconds for a complete oscillation. So the definitions are very nicely reciprocal. I'm sorry this isn't prettier. So, these should look somewhat familiar if you took physics before.
We can go back to
Half. Got it? Okay. Now the period of a pendulum, we're actually going to see 2 major categories of simple harmonic motion. We're going to see the simple pendulum, and we're going to see masses on a spring. They aren't the only major cases of simple harmonic motion, but they're the two most common cases of simple harmonic motion. Notice that I did say the simple pendulum. From now on, I'm just going to call it the pendulum. But please note that not all pendulums follow simple harmonic motion. We're going to talk more about that in a second. The formula for the period of a simple harmonic motion, for a simple pendulum is 2 pi times the square root of L over G, where L is the length of the pendulum and G is the acceleration of gravity wherever that pendulum is. Yes, sir?
Doesn't this only work for like when it's less than 30 degrees?
We will get there. This is why I said that I am specifically pointing out that this only works for simple pendulums and not all pendulums. But we're going to talk more about that in a second. Very, very, very similarly, the period for a mass on a spring is 2 pi square root m over k, where m is the value of the mass that is attached to the spring. Usually, we assume that the spring has a mass of what?
0.
Yeah, 0. Just like pulleys, just like strings, just like ropes, we normally assume that these things are massless so that we don't have to worry about them. K is the spring constant. There's a little asterisk down here that says you should be able to derive these. Not yet, but we will. We will actually be able to derive these in a second. In a little bit, we will be able to derive these. Well, maybe not a second, but before the end of the class.
What's the oscillating mass on a spring? Like, what is it?
Well, remember that oscillating means we're cycling back and forth doing the same thing.
So is it also a pendulum?
No, a pendulum swings back and forth. This is a mass on a spring that's just cycling back and forth in the direction of the spring. I'm going to show you some pictures of what that means in a second. Something that's really important to remember, and it's a place that will guaranteed get somebody. I don't necessarily mean somebody in this class, but somebody sitting for the AP exam is going to fall for this. More than one, I know this, but it's going to happen because it always happens. The spring force is what? Anybody remember what it was? Kx, which means it is what? It depends on x. If it is, and I'm going to change this, I'll come back in a second. If it is oscillating, that means it is moving, which means x is changing. That means F is changing. So that spring force is a variable force. It is not constant. So setting it equal to MA and thinking that A is constant is not great. There are certain things that are true about this relationship at certain points in time, but not as a whole, and we're going to take advantage of that. So you're right.
Isn't it like in the middle, kinetic energy is radius?
We're going to fill that out in a second. But I keep saying in a second. I don't know why I say that. I guess I'm going to use a cosmic second. Is what I'm really thinking. It's a variable amount of time. I'm not. Don't even bother. I don't care about this anymore. I don't have the time. I don't want to do it anymore. Blah 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 blah. I don't care. Okay. A lot of things cycle. The first thing I said when we started, if you live in South Florida, and you've been living in South Florida for long enough, you've got an oscillating fan. If you grew up in the 90s, you've got probably one of those sprinklers that cycle back and forth. But that does not. But it's not like kids nowadays don't have any joy. You know what I'm saying? Like.
Wait, the sprinklers as in like the ones that water the trees?
No, I'm talking about Back when I was a kid,
like
that was a toy.
yard, like the-
That was a toy. Like you did not buy that to water your yard. You bought that because you didn't want to take care of your kids and you wanted to let them go outside and play. That's what you did. So, and my family was poor, so we didn't have that. We just had a hose, and it was just like, just go outside and hose yourselves down, but not for too long because we pay for water. So there's a lot of things that cycle, that kind of do the same thing over and over and over again. But that does not mean that they are all simply harmonic. The oscillatory part is only a very, very, very small piece.
I found like this sitting in the other room.
Yes, thank you. The oscillatory part is only a small piece of the requirements for something to be called simply harmonic motion. And that requirement is that it must have, back and forth motion, blah, 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 that goes through an equilibrium, blah, blah, that part we already knew. It has to oscillate, blah. But it must have a restoring force that depends on the displacement that the object has away from equilibrium. Put another way, it kind of needs to look like that. So very quickly you can see that the spring force satisfies that requirement. It is a restoring force. We know that because of the negative, right? It does depend on the displacement away from equilibrium, and we know that because of that delta x. That should be a delta x. Sorry. That's what I get for being fast.
But if you're doing, like, let's say you do delta, you can't really do delta x because if you start and end at the same point.
Remember that the delta x for this formula is specifically defined as the distance away from equilibrium.
Right, so.
Not just from where you start, right? But yeah, if it was from wherever you started, then it would be zero, there'd be no force. So this is the important condition that you need to satisfy in order for any oscillatory motion to be classified as simply harmonic. Anything can be oscillatory, anything. But if it does not have a force that depends on its position away from equilibrium, it does not count as simply harmonic. What's an example of something that is not or something that is? That is not, again, the fan, going back and forth. That is not, does not have a force that puts it back towards equilibrium. What would be another example? A CD spins round and round. That's oscillatory, right? But it doesn't have a force that puts it back to equilibrium. Right now, my foot is swaying back and forth over and over again, but that would not count as oscillatory, mostly because I'm the one that's causing it, not some other force. A propeller.
Does it need to be a linear relationship to x, or it can be any?
Directly proportional.
Oh, so that's okay. That's actually.
Can we keep going? So, in the case of a mass on a spring, for example, if I had a horizontal mass on a spring system, very often it'll be attached at one end. The maximum distance away from equilibrium is often called A for amplitude. Very often called A for amplitude. Let's take a look at certain things that we already know. When my system is at the amplitude, right? What does it have? When that spring is at the amplitude, what do we know?
Full restoring force.
It has a full force. So all the way out here,
And zero velocity.
the force is maximum.
Velocity zero.
The velocity is zero. If the velocity is zero, what does that mean?
Acceleration is not acceleration.
Well, yeah, but if specifically the velocity is zero, what does that mean? Kinetic energy is zero. Okay, so if the force is maximum, which means, well, this is because delta x is maximum, and that means U spring is maximum. But then this also means that acceleration is maximum at that point. Well, if the force is maximum, And then we can use Newton's second law and say F equals ma. At that point, I can't use it for the whole thing, but if I freeze frame and look at that point, then I could say A would be maximum. Because kinetic energy depends on what? Velocity. Acceleration is not velocity. It's the rate of change of velocity. So that means that at that point, I will end up getting the biggest possible change in velocity the next second. And then the second after that, it'll be a smaller change, but it's still going to be a change. The second after that, it'll be an even smaller change, but it's still going to be a change. Right? And that's what I'm going to end up seeing. As this thing starts to travel that way, that's the way it will move. That's the way the force is pointing. So it's going to move to the right. What happens to delta x? It decreases. So as it moves this way, so delta x starts to decrease as it goes that way, which means A starts to decrease because F starts to decrease as it moves that way. But then that means that
Delta x is the distance away from equilibrium.
yes.
Isn't it increasing?
Well, here's equilibrium right here.
G is maximum, your potential
But equilibrium is right there.
Oh, okay.
So right there, it's far away from equilibrium. And as it's moving that way, it's getting closer to equilibrium, so its delta x is getting smaller. And if its delta x is getting smaller, its force is getting smaller. And if its force is getting smaller, then technically its acceleration is getting smaller. But if its delta x is getting smaller, its potential is getting smaller.
It's kinetic energy. They have to tell you what point.
Yeah, they should.
So K is maximum.
Then k is getting bigger, which means v is getting bigger. And then when it gets to the maximum, to this point, this is happening, all of this is happening as it moves to the right, as it's moving to the right. But when it gets here at equilibrium,
Kinetic energy is maximum.
k is max, the velocity is max, U spring is not just minimum, but it's actually 0. Delta x is 0. The acceleration is 0. The force is 0. That looks like a 6. 0. Okay. And then it's going to go where? It's going to keep going to the right because it has, that's true, kinetic energy, but it also has inertia. And its inertia is going to tell it to keep going the way that it's going. It originally was going to the right. Its inertia is going to say keep going to the right until there's an outside force. And as soon as it starts going to the right, what starts to happen? What's the first thing that happens, though? Okay, so the first thing that happens as it goes to the right, this is as it goes to the right. And here, as it goes more right, then delta x increases again, which means the acceleration will increase. But in this case, it's going to start to increase in the opposite direction. It's going to start pointing to the left. And in the beginning, it's going to be a very small arrow, but pointing leftwards. My velocity vector is pointing rightwards. As it goes to the right, I'm talking right before I get here. As it goes to the right, my velocity points to the right, but my acceleration is starting to point to the left, which means my system will slow down in order to change direction. So my acceleration is going to increase, my force is going to increase, my velocity is going to decrease, my kinetic energy is going to decrease, my spring potential is going to increase because my delta x is getting bigger. When it gets to this amplitude, not only am I the same as that one, but I'm also now flipped. Over there, I had an acceleration that was maximum, but actually it was positive. It was to the right. Here, this is same as the negative amplitude, but
Are you allowed to say that the
flip side.
Are you allowed to say that the restoring force between the two is a third law pair, or because
No, they're not third law. Third law pairs happen on separate bodies. It's the same body, but you can say it is literally the same force, except it's in opposite directions because, again, restoring forces want to go back to equilibrium. Before, in the beginning, at that negative amplitude, back to equilibrium meant right. So the force pointed right. At this positive amplitude, back to equilibrium meant left, so the force is going to point left. And then this guy is going to do the same thing that this one did, but flipped signs. And then this guy, no, at equilibrium, it's going to do the same thing that this did at equilibrium, but flipped signs.
If there's no friction, it's going to keep going.
Yeah, it'll do the same thing over and over and over again. And I'm going to have a case of kinetic turning into potential, turning into kinetic, turning into potential, turning into kinetic, turning into... And you get my drift. You get what it's going to do. And this is a horizontal system. If I have a vertical system, not a lot changes, except I get the addition of...
Why?
That's true, y, but I also get the addition of gravitational potential energy. That would be the difference. Now, this system will usually stop. It will come to rest at some equilibrium position when what happens?
When mg is greater than y.
Well, if it was greater, then
Well,
it would have an
when it's
acceleration.
equal.
When the weight of the system is equal to the spring force up, then this thing will end up being at rest. So that was the first case, the mass on a spring. Okay, chilling, not bad. This one is a little bit trickier. You guys had Felipe last year. Did he prove this? Or did he just tell you this?
why it's simpler?
Yeah, why this is simply harmonic. No? Okay. So we're going to prove why it is simply harmonic.
If you show what the restoring force is, you can show that.
So, is a pendulum an example of simple harmonic motion? And the answer is yes, it is.
Oh, I think
Because what we can do is redraw that force. If I look at the pendulum, the force that's acting on this part of the pendulum, that's called the bob of the pendulum, for the record. It's the mass at the end, is what force? Or what force is? Tension, which points along the line of the rope, and gravity pointing straight down. Now, equilibrium is actually in this direction. It's that way. For the bob, equilibrium points this way because it wants to come back over here towards this line of 0 where it is not displaced. Everybody sees that?
Yeah.
If I break apart this gravity vector, just like we did with the ramp by rotating our coordinate system a little bit, what we'll see is that the y component of gravity, mg cosine theta, cancels out with my tension force. That makes sense because my bob doesn't fling outwards, right? That tension force is what's keeping the bob still in its motion, in that centripetal motion. But this x new rotated coordinate system, x component of weight, does not cancel out and points in the direction of equilibrium. So I end up getting this restoring force that looks like mg sine theta. And you can ask, let me just take it, okay. You can ask yourself very quickly,
This is where the angles don't count.
well,
Because they're so small that
hold on, before that argument, you can ask yourself very quickly, mg sine theta does not look a lot like k delta x. Because what we needed was a force that is directly proportional to the distance away from equilibrium. Now, this is pointing towards equilibrium, which is good, right? It is good. I could make some argument that m could be some placeholder for k, right? To be fair, directly proportional just means multiplied by some constant coefficient, right? That's really what that means. But g sine theta in this current form is not a directly proportional to distance term, right? So what we would need to do is a little tiny bit of trigonometric trickery. A little tiny bit of trickery. Because we can replace sine theta with theta if, and only if, the angle is small. It's called the small angle approximation. And if I have small angles, whether it's measured in radians or degrees, whatever, and I plug in my number, what I'll get for the value in radians and what I'll get for the value of sine is actually really close for small angles, right? So if I plugged in 1 degree, which is 0.01745 whatever in radians, if I plug that into my calculator, I will get that number, which is a very, 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 very small percent difference. If I plug in 10 degrees, I get a 0.5% difference. If I plug in 30 degrees, I get a 4.5% difference. So it's not that crazy. Usually, we're kind of chilling in that range of 10 to 15 degrees for a simple harmonic motion. That's usually where we are. And the reason why that works is because of that Taylor series of sine. Because that first term, look at that first term, sine of x could be approximated by x if the x's are small, when the terms are small, if you start putting in bigger terms. And that's why we have these bigger terms here to start making. Remember, you guys, for sure, I saw Gabby do this. Remember, Ms. Slapak, she showed you the limit of sine of x over x approaches 1, because for those small numbers, sine of x and y equals x behave very, very similarly for small numbers. But as my numbers get bigger and bigger, I need to start adding more terms to my Taylor series so that I can force my not sine line to get closer and closer to my sine line, right? But if I don't make big angles, why do I need all of these terms, right? So that's what we do here. And we make another small little change. We're going to replace this sine theta with, what is it? Opposite, which is this distance Raher over hypotenuse. And if I do that, then I will definitely have a force that is dependent on distance. It will specifically be this distance right here. Right? Everybody kind of sees what I'm talking about there? Yeah, yes. Yeah. So is everybody cool with that? So yes, indeed, certain pendular motion, I don't even know if that's a word, it just sounds good, can be simply harmonic. We just have to have a couple caveats to it. The angle can't be very big, and then we have to make a little replacement here. But that's okay. That's not a big deal. But I mean, when the angles are small, even 10 degrees, 0.5% is not a big deal. It isn't. Especially when, if you think about this, if you're in the real world, if you're in engineering, look at this decimal place. The difference between the angle and sine of the angle only really makes a big difference in the thousandth place, right? Milli? Really?
Wait, when do you ever need pendulums in real life? Do you ever have to...
Grandfather clocks is the easiest example, but there are other places where pendulums show up that are useful. What? Yeah, you could see them in a lot of other places, but I mean this isn't only true for just that. But this approximation shows up in a couple other places as well that are not just pendulums. I bet you guys that we're not expecting to see Taylor series. Yeah, buddy. Now, a couple slides ago, I did say that you would be able to derive those equations for the periods. This is where we're going to start to be able to do that. Systems can be defined as simply harmonic, the way that we already did, right? It depends. It's oscillatory and it has a force that is dependent, linearly, directly dependent to the displacement away from equilibrium. That is true. That is very true, and that is a very physics definition. But if I have not made this point home all year, I'm hoping I make it now. Mathematicians, with their dirty little grubby fingers, have another way of defining simple harmonic systems. And if the system produces a differential equation that looks like that, then it's simply harmonic. That's actually all they need. They don't care about it physically. If the differential equation looks like that, it's simply harmonic. Bam, period. That's it. That's all they need. And we can actually get there if we start with F equals ma. And this is making let's make a small understanding. Let's omega, which was angular velocity. But let's make a small understanding. Number one, if we do F equals ma, let us understand that a is not a constant acceleration. It can be a changing acceleration. Okay? That's the understanding number one. Understanding number two, that if we say F equals ma, then I do not necessarily need a to be a constant acceleration. I don't need that to happen necessarily. I don't need it, but it's nice. Number two, this does not necessarily need to represent a spring. This can represent any system that is a restoring because it's negative, restoring force that depends on distance away from equilibrium. Can we be cool with that? And this K can represent any constant of proportionality in front. All right? Is that cool? If we do that, and we set these two things equal to each other, I get something that looks a little bit like that. Right? Now, because we are a calculus class, we know that acceleration is the second order derivative of position, correct? So I can replace a with d2x dt squared. Right? Right? I can do that. And if I bring this negative kx over m term to the other side, then I'll get this equation right here. d2x over dt squared plus kx over m. That's what I'm going to end up getting.
But it doesn't satisfy that equation.
No, hold on. Wait. We're just getting there. Okay. Now, this is a differential equation. Duh, because differential, right there, derivative, right there. Now, not only is this a differential, we've made a couple small, tiny substitutions. The difference between here and here. We've replaced k over m with omega squared. A small arbitrary substitution for math reasons. We've substituted for math reasons, small math reasons that we've done this. But what that tells me is that what did she say? What did they just say?
No, it's funny because it's just so embarrassing.
Do they know that window's over?
What? I don't get it.
Oh my god. Okay, so if I do this, then we can say that omega is equal to the square root of k over m, right? We can say that. Don't worry about the y's for just 1 second. It's okay. We'll talk about it in a little bit, but we can say that. And then what we can look at this, take a second, think about it. Just think about it in your head. If I bring this back to the other side and leave it alone for a second, what function can I take a derivative of twice and get the same function?
E to the x.
E to the x is one of them. It is not the only one, though. There is one other one.
Without negative.
Sines
But you get
or
negative.
Or cos. Well, yes, I will get a negative, but if I do move this over, I do get a negative. Also, technically, I mean, if these are constants, they could be constant. They could be negative constants. They could be.
Right, but like the second derivative of sine is negative sine.
Yes, and if I bring this over to the other side, I will get a negative. This is plus omega squared x. So if I bring this over, it'll be negative omega squared x.
Negative, so it's positive. Oh, I get it. And then
No,
you take out the negative.
Right? You with me so far?
Yeah, I got it.
So this is a very, very special type of derivative. And there's technically two types of solutions. There's the exponential solution, and then there's the sinusoidal solution. Actually, it turns out they're the same. Exponentials and sines are the same. Using Euler's identity, sines and e to the I theta, you could turn that into sines. So you can get the same thing. But turns out that we can get a solution to that differential equation using some common sense, not using some math. If I take the derivative of a function twice, I get itself. That only happens with two functions, e and sine cosine. So very often, that's exactly what we do. The function could either be a cosine omega t. Don't worry about the omega t for 1 second. I'll tell you why in a minute. Or technically, it could also be a sine omega t. It really depends on where is the motion of this function. Where is the object when t equals 0? So if the object is at the origin at t equals 0, then it's a sine function because that's where sine functions start. If the object is at amplitude, well, not necessarily 1, but yeah, amplitude, because it doesn't have to be 1, but at t equals 0, then it's a cosine function. Then things are tricky. But that's not something we have to worry about, not really. Now, an interesting thing to notice in a second, does anybody remember what a omega represented? Let me rephrase that. What does a represent? Amplitude. In other words, it is the distance away from.
the 0
So it's not an acceleration actually.
times the angular velocity.
Distance away from the center to the point times
It's
angular
VS.
velocity. So this is a velocity in the
Velocity times distance.
Circular.
in the linear world. I have it right here. V equals,
radius.
or it's like the radius.
Okay,
So
okay.
this is the linear velocity. Anybody? This one might not be so obvious. That one is a little trickier.
Oh, isn't that centripetal?
Yes, that is the centripetal acceleration. R omega squared or V squared over R is a centripetal. This is the centripetal acceleration. No, what I'm saying is if I take, remember, a centripetal was V squared over R.
Yeah.
If I take this equation, this relationship for V, R omega, and I plug that into V squared over R, what I'm going to get is that. R omega squared. Remember that, for the record, I think I only told David because he was the only one that was here. R in physics does not mean radius. And originally, R never meant radius. R meant a distance starting at the origin. That's what it meant. But when we defined all of the relationships for things like volumes and areas and all of this stuff, a lot of shapes are circular and depend on the radius. And people are lazy, and they went, radius starts with R, so that's what we ended up doing. We conflated R with radius. But it does not mean radius. It really just means a distance from the center, for the record. So there is a connection between simple harmonic motion and circular motion. That's kind of a reason why we do these back to back. If we started with the position function and we take the derivative of these things to find velocity and acceleration, what I end up getting is something that kind of looks like this. You okay? You want to go outside, get some water, get some fresh air? You want to smell the strawberries? Shove your face in them. Is everybody okay with the A omega term that comes in front?
Yeah, because that's like a velocity, so it makes sense you end up with a velocity.
That is true, but it also comes just from the derivative because we have to do chain rule. We got to do the chain rule, so I gotta multiply by the inside, which is an omega on the inside. If I take the time derivative of omega t, what is the derivative of 3t? 3, right? So then I have to multiply by 3 in the front. So if I take the derivative of omega t, then I have to multiply by omega in the front. That's why it's still here. And then when I do that again, I'm going to get another term of omega, and that's why I get an omega squared here at the bottom.
I don't get the purpose. So he somehow went from that initial differential equation, and you're going on this whole thing about how we want it to go back to itself, but I don't get where you're going.
No, well, that original differential equation is useful because what this is, it does not tell me what the function of x is. Okay? It just tells me that whatever the function of x is, if I take the derivative of x twice and I add it to itself times omega squared, I'll get 0. That's it. That's all it's telling me. So then, if I want to know what that original function is, the logic is, what function do I take a derivative of twice and get itself? There's only 2.
Why did you say itself?
Well, if I bring this term to the other side, I'll get something that looks like this, right? I'll get d2x over dt squared equals negative omega squared x. So take the derivative of x twice, and you'll end up with some coefficient times the function x. So what function can you take the derivative of itself twice and end up with the same function, but the only difference is a coefficient? Try it with x cubed. Try it with x cubed. Take the derivative of x cubed once. Okay, 3x squared. So dx of x cubed is 3x squared. One more time. 6x. Okay, so dx of 3x squared is 6x. So that means that d2 dx squared of x cubed is 6x, right? Which is not the same as x cubed times a coefficient. It's not the same. So it can't be a polynomial function. Polynomial functions don't do that because they always reduce in order. It can't be something like a logarithmic function, because what's the derivative of a logarithmic function? Yeah, 1 over x, so that changes. It can't be, what other functions do you guys know about? A radical, right? It can't be a radical.
That's the same thing.
Yeah, polynomial, whatever. So the only options that we have in terms of derivatives, e to the x, if I take a derivative of e to the x, I'll end up with e to the x again. So that does do that. So it could be an e to the x. Sine and cosine also do that. They kind of go back and forth. So the real answer would be to work through this and actually do some differential equations so I could differentiate between whether this is an e to the x function or whether this is a sine or cosine function. And the honest answer is this is actually an addition of e to the x functions that turn into a sine or cosine function, because that's how sine and cosine functions are. So now that we've defined what the x function was, that position function, I can just apply the definitions of position, velocity, and acceleration, which are rates of change, and get the velocity and acceleration functions for simple harmonic motion situations. Now, the only thing that I want you to just bear with me for 1 second is this omega t term. That's the only thing I want you to bear with me. If you remember rotational motion, you should kind of already know what that is, because what do sines and cosines need? An angle. They need an angle. Guess what omega t is? Yeah, it's an angle. That's what omega t is. It's an angle. But just bear with me for just 1 second, and then I'll prove that. Now notice that A is an amplitude. That's all it is. It's just an amplitude. Now graphically what that means is the displacement function If it is a, what is that? What is that?
Oh, that's a cosine.
It's a cosine, and this one is a sine, and then this one would end up being a negative cosine. And what you're going to see is that the displacement and the acceleration functions, they actually kind of match together, and that's what we saw. Bam, 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 bam. That's what we saw here. The displacement was max, and the acceleration was max. They happen to be max together. The only thing is they are opposite. So when the acceleration is max positively, the displacement is max negatively. It makes perfect sense when we think about the fact that these are restoring forces. If I am the biggest I can possibly be to the right, my force is trying to push me back to the left. That makes sense. But it's nice that not only does it make sense physics-wise, it also comes out in the math. And that's the important part. 10% battery remains. All right. Now, okay. So if we replace omega t, if we replace this from its linear terms of a, which is the amplitude, to an angular term, the maximum angle, we'll get an equation that's exactly the same. It doesn't matter. It's the same thing, except instead of the maximum amplitude, it's the maximum angle. Don't worry about that just yet. Now, a couple of things that we saw in the beginning that we're going to tie together. Omega t, we said, was theta. It is the angle. If we look at this in terms of units, this is radians per second times seconds is, I don't know why I thought radian starts with S. Radians. So omega t is radians. That makes sense. Now, how does 2 pi frequency give me omega? Oh, that's kind of useful. I would not go with the units. What's another way for frequency?
It's the amount of times. It's the time in a cycle multiplied by the length of the cycle.
Exactly. Omega, we said, was the angular speed, angular velocity, same thing. And if my system is moving at a constant velocity, then how can I define velocity? No. Distance divided by time. If there is no acceleration, my velocity is a constant number, which is distance over time. Well, what is the distance of a sine function? 2 pi. As long as the function is not, stretched or compressed, right? It's 2 pi. Now, what is the time it takes to do that? Well, no, the period. The time, I don't know what number is. I don't know. But by definition, I know that it is called the period. So technically, this should originally have been written like this. That's what it should have been written. But then, exactly. But then I know that, so I can replace this with that. That's nice. And then that means that there's a couple different ways that we can rewrite these position functions depending on the information that we're given. So we've got a lot of power. If they give me frequencies, then we're not stuck. We can make certain assumptions here. Now, there is one major thing that you do have to keep track of that can be really confusing, and that's this last one right there. That one can suck a little bit. Anyone want to tell me why? Yeah, T and T. And not the channel, but this T is not a variable. It is a constant. It represents the period. It's a definite number, and this t is a constant. Right there. So what I'm saying is, like, these are all the different ways you could write it. It really just depends on what information the problem wants to give you. Now, they could totally have just given you this formula and then said, hey man, these are all true. Good luck. But, I mean, it's easier. It's a good thing I don't have an iPhone, otherwise that would be a cracked screen. Oh. Whew. Okay, so that's nice that they did that for us. We already said that. So whether the function starts at 0, where the function starts will help me figure out if it's a sine or a cosine function. Now, getting that period thing is a matter of knowing what that omega is. Remember that in that differential equation, we had made that small substitution where we had that k over m term, and then we just replaced that with omega squared. Well, if I kind of work my way backwards, we said before that omega, that angular speed, was 2 pi f. I can kind of replace that a little bit with 2 pi over period, right? And if I follow through with the algebra a little bit and isolate for period, and then make that substitution back out to get rid of omega, I'll end up getting the exact equation that we had before.
How did you put omega back?
How did I put omega? Well, omega is, from this equation, omega is 2 pi f, right?
Yeah.
Or 2 pi over period.
Sure.
Okay, so that's what we had here. Omega equals 2 pi over period.
Yeah.
So bring period over and divide by omega. So I get period equals 2 pi over omega, which makes sense. Time is distance divided by velocity, right? But from that differential equation that we started with, where did it go? Was it before all this? Was it It was after. Sorry. I skipped it. I don't remember. From that differential equation, we made that really quick substitution where we said that omega squared is going to replace k over m. So that means that omega is the square root of k over m. Just take the square root of both sides. And if I do that, and I plug it back in here, and it's for the math. There's no real physics answer. Give me a second. Okay, I'm not going to lie to you. I don't remember the physics answer because it's been a long time. I will find it for you. I'll find it for you. My teacher, when I first started this, told me it's because of differential equations. And then when I got to my differential equation class, my teacher told me it was because of physics. And then I never actually learned the reason. And then about 4 years ago, I looked it up and I got a reason, and then I forgot it. So I will look it up. I know there is a tangible reason why they switch it to a squared. I don't remember why. I will tell you. I will look it up. And then I'll end up getting this. I know for sure it has to work out unit-wise because K is newtons per meter. So that's going to end up giving me meters squared somewhere. I'm going to end up, actually, I'm going to get more than that. This is going to end up being meters over newtons per meter, which is kilograms meters per second squared, which this is going to cancel with this. Oh, no, that's mass. Whoops, that's mass. Sorry, kilograms. This is going to cancel with this, and then this goes to the top, so taking the square root of second squared is seconds. Yeah, so I know it has to be there for the units, for sure. I don't remember the actual mathematical or more physics reasons than that.
The question is why there's a square root?
Yes. So I know there's got to be a more tangible reason than the units have to be there. So without the square root, the units would not work. I will find out. Now, the force is directly proportional to the displacement. We already said most of these things, so I'm not worried too much about that. If I gave you this, I think this is the last thing we have time for. If I gave you this, let's write the equation of motion for this. We'll write the position one, and then we'll write velocity and acceleration, and then we'll graph them. Okay? So, really quickly.
Why are we going to graph this? Oh, like
Well, this one is position, so we're going to graph velocity and we'll graph acceleration. So, position. Okay, what? How do you know it's 4? How do you know that?
From the distance from the origin to the highest points, I guess, are
Right? You guys see that? Oh, is that the bell? Are we done? Okay. So we'll just write the function for.
Sine starts at 0.
Okay. So now we got to figure out what we want to graph. What do we want to graph? This is a time.
Well, you know your variable's time.
Yeah,
You know
that
your
is a time.
period.
What is my period?
Well, you not really. It's kind of hard.
It's a little hard. I mean, that's not terrible.
It's like 3.1.2.
No, 2 point.
No.
Oh, no, you're right. It's 3 point.
So I could go with, where are we? We could go with omega t, but the problem is we don't know omega.
Right.
We could go with 2 pi frequency. The problem is we don't know frequency.
Or time.
So let's go with 2 pi over t and make a pretty good educated guess with t. That's not a bad... Well, what information from this graph will tell me frequency? Cycles per second. So how many cycles does this do every second? Well, we do have times. We do have times. So,
I mean, just 1 cycle per second. Isn't it? No. Sorry.
well, 1 cycle here.
1 cycle per 3.1 seconds.
Are you sure that's 3.1? 3.1. Okay. So what I'm saying is if we do frequency, we're going to have to make some guesses on time. If we do period, we're going to have to make some guesses on time. That's okay. Not a big deal. Which one do you want to write? Frequency or period? Which one do you want to use? Frequency. So then I'll write 2 pi times, what is that?
1 over 3.
Which is? You guys have calculators, man.
Like 1/3, so
Yeah, probably a little bit smaller than 1/3. We can multiply 2 pi times all that and get a number, but I'm not too worried about it. What would the velocity graph? Where would the velocity graph start?
Where would it start? Well, sine would start at 4.
It'd start at 4. And what would the acceleration graph start at?
It would start at 0 again, but it just be reflected over.
Wait, is it possible that the period is actually pi? It looks like 3.14.
It's possible.
So we could actually just cancel those out and get a pretty exact number.
Should be pretty close. I think the period is pi.
Yeah.
All right, guys.